Quantum computing. You've heard the term, right? It sounds like something straight out of sci-fi, promising to solve, well, everything. But what is it, actually? Are we on the verge of a massive breakthrough, or is it all just hype? Well, over the next few minutes, we're going to break it all down and demystify this incredible technology. All right, so here's how we're going to tackle this. First, we'll look at why we even need something beyond our current computers. Then we'll meet the star of the show, the quantum qubit. We'll see how it gets its power, what we could do with it, and finally, we'll get real about the hype versus the reality. Okay, first up, beyond the binary bit. Let's talk about why your laptop, powerful as it is, just can't solve everything. So everything you're using right now runs on what's called a classical bit. Think of it like a light switch. It's either on or it's off, 1 or 0. Simple. But a quantum bit, a qubit, that's a whole different ballgame. It's more like a spinning coin. Before it lands, is it heads or tails? Well, it's kind of both at the same time. And that's the magic right there. All right, let's meet this new hero of computing, the quantum qubit. We've got to understand this spinning coin a little better, because this is where things get really weird and really, really powerful. So a qubit is the fundamental building block here. And unlike a simple bit that's just a 0 or a 1, a qubit state is way more complex. It's not just on or off. It can be any combination in between. Imagine a sphere. It can be pointing anywhere on the surface of that sphere. This is how it can pack in so much more information. This leads us to its first superpower, superposition. This is that spinning coin state we talked about. It's the qubit's amazing ability to exist as both a 0 and a 1 at the exact same time. But here's the crazy part. The moment you look at it, the moment you try to measure it, poof, the spinning stops and it's forced to pick 1. It collapses into either a definite 0 or a definite 1. Okay, you thought superposition was weird? Hold on. Let's talk about entanglement. This is where things get, frankly, spooky. You can link two qubits together in this special way, and from that moment on, they're connected. If you measure one and it becomes a 0, you instantly know the other one's state, no matter how far apart they are. Across the room, across the planet, it doesn't matter. It's like they're two sides of the same coin, even if they're light years apart. So we've got these two bizarre mind-bending properties, superposition and entanglement. What does that actually get us? Well, this is where we see the parallelism promise, how quantum computers get their superpower. Okay, this is absolutely key. With a regular computer, if you add one more bit, you get, well, one more bit of power. It's simple addition. But with a quantum computer, it's totally different. Every single time you add just one more qubit, you literally double its computational space. It's not addition, it's exponential growth. And that exponential growth leads to numbers that are just impossible to wrap your head around. Let's say you have a 100-qubit system. To represent all the information in that system on a classical computer, you'd need 2 to the power of 100 bits. You know how big that number is? It's bigger than the number of atoms in the known universe. Yeah, let that sink in for a second. That's the power we're talking about. So, okay, we have this theoretical machine with almost infinite processing space. So what? What could we actually do with all this power? Let's talk about solving the unsolvable problems. I mean, the possibilities are just staggering. We could design new medicines by perfectly simulating molecules, something that's impossible today. We could create new materials with incredible properties. We could solve insane logistical problems, like optimizing global shipping routes in real time. And yeah, then there's cryptography, the one that gets everyone a little nervous. This is the big one. See, back in 1994, a mathematician named Peter Shor came up with an algorithm. And this algorithm, running on a big enough quantum computer, could basically shatter the encryption that protects, well, everything. Your online banking, your emails, your private messages. All of it is built on a type of math that's just too hard for our current computers to crack. But for a quantum computer, it's like a hot knife through butter. All right, so if this thing is so powerful and could break the internet, why don't you have a quantum MacBook on your desk? This is where we need to pump the brakes and talk about the huge gap between the hype and the reality. This quote from the journal Nature last year really says it all. For now, what are quantum computers good for? Absolutely nothing. It's a bit harsh, but it's true. For all the promise, not a single quantum computer has solved a real-world, practical problem better than your laptop can. So what's the deal? The number one enemy,
the biggest challenge by far is something called decoherence. Remember how powerful that fragile spinning coin state is? Well, it's super fragile. The tiniest vibration, a bit of heat, a stray particle from space, anything can knock it over. And when that happens, the quantum state is gone and your whole calculation is ruined.
And trying to stop decoherence is one of the hardest engineering problems on Earth. We have to keep these things in giant refrigerators that are colder than deep space. We're talking just a sliver above absolute zero. Even then, the quantum state might only last for nanoseconds. And get this, to make just one stable, reliable, logical qubit, we might need to link together thousands, maybe even 1,000,000 of these messy physical ones. It's a monumental task. This all feeds into this huge debate around quantum supremacy. That's the moment a quantum machine does something a classical one can't. In 2019, Google made a huge splash claiming they'd done it. A calculation that would take a supercomputer 10,000 years, they did in 200 seconds. Sounds amazing, right? But then IBM came back and said, hold on, our supercomputer could actually do that in about 2.5 days. And the thing is, these are very specific, custom-built problems. They're benchmarks, not useful calculations.
So that's really the heart of the matter, isn't it? On one hand, you have this beautiful, revolutionary theory that promises to change everything. And on the other, you have the messy, practical reality of building these incredibly delicate, error-prone machines. There's just a massive gap between the dream and the reality right now.
And so that leaves us with the big question, the one everyone in this field is trying to answer. The theory works. The potential is, without a doubt, world-changing. But the engineering hurdles are just gigantic. So will we overcome them? Will we finally bridge that gap and build the machines that redefine our world? Well, for now, that's the great unsolved problem.